Tudum tudum tum 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 la 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 Emma's world tum 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 la 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 Emma's world tum tum tum. You will learn physics 'cause I teach you in Sir Emma's world. Okay, so today's lesson is all about the laws of thermodynamics. Hooray! So, as usual, as per, well, tradition, we would have our Guess the Drawing segment, okay? So, here's the drawing that you are supposed to guess. So, what is this? Again, so to be able to guess the drawing correctly, we have one winner for each class. So, whoever guesses correctly shall get one bonus point. Okay? So let's now move on to our lesson, which is the laws of thermodynamics. So what are the laws of thermodynamics anyway? So let's see. So yeah, there are four laws from thermodynamics, okay? And practically, well, they're not named law number 1, 2, 3, and 4, but we have a zeroth law per se. So what does the zeroth law of thermodynamics tell us? So the zeroth law of thermodynamics, also known as the law of thermal equilibrium, okay, states that when two systems are in thermal equilibrium with a third system, then the two systems are in thermal equilibrium with each other. In other words, suppose we have this system A and B, okay? A and B are separated by an insulator, okay? So this thick line here, this is an insulator. So thermal conductivity between A and B is impossible. So they do not interact with each other thermally in any way whatsoever. And then both systems are, well, thermally in contact with system C. So according to the zeroth law of thermodynamics, if A is equal to C, okay, if A is in thermal equilibrium with C and B is also in thermal equilibrium with C, then most probably A and B are in thermal equilibrium with each other. OMG. Okay, it's just like in mathematics. What law is that? Transitive? Is that transitive? Anyway, so what's the purpose of the zeroth law of thermodynamics? The zeroth law of thermodynamics helps define the notion of temperature. As temperature, as we all know, is measured by a thermometer, and the thermometer is in thermal equilibrium with that of the body or system whose temperature is being measured. So that's basically how a thermometer works. For example, when a thermometer is in contact with air, the temperature reading in the thermometer is in thermal equilibrium. The temperature of the thermometer is in thermal equilibrium with that of the air. Okay? Because that is the system in which the thermometer is in thermal contact or in thermal equilibrium with. So basically that's how the zeroth law of thermodynamics works. Okay, it's all about thermal equilibrium. That's why it's known as the law of thermal equilibrium. The next law as you would see here, okay, would be the first law of thermodynamics. Okay, so the first law of thermodynamics is preceded by the zeroth law because, okay, let's see, let's have a little bit of history lesson here. Actually, the first laws in first thermodynamic laws that were discovered were the first, second, and third laws of thermodynamics. However, later on, another law was, well, another law was discovered, the law of, well, as you've guessed it, the law of thermal equilibrium. And the scientists noticed or observed that this law, the law of thermal equilibrium, is precedent with that of any of the three laws that were previously discovered. So instead of naming it the fourth law of thermodynamics, they named it as the zeroth law of thermodynamics. Okay, so that's enough of scientific history. Let's move on back to our lesson. So let's go back to the first law of thermodynamics, also known as the law of energy or the law of conservation of it. Well, no, it's not really the law of conservation of energy. It's something to do with that. Anyways, So let's have the first law. According to first law, heat and work are forms of energy transfer. Like duh. And the change in internal energy of a system is given by the following equation. We have here the change in internal energy, delta E int, internal energy, that stands for the change in internal energy, is equal to the done, heat by the system, or heat transfer inside, away from the system or to the system, plus the work done by the system or work done to the system. So practically, the first law of thermodynamics is essentially a restatement of the law of conservation of energy. It's a statement of the law of conservation of energy. Okay, so according to, as we all know, energy cannot be created or destroyed. It just transforms from one system to another. And this law tells us that the internal energy, or the energy inside the system, is equal to the heat done on the system plus the work done on the system. Okay, when it's heat, the heat that is given to the system and the work done. So that's practically the first law of thermodynamics, a restatement of the second law. If we have the work, if the work is done on the system, meaning it means that you are adding energy to the system, then the sign for this is positive. When work is done on the system, the sign for it positive. If it is done by the system, the sign for this is negative, because you are, well, giving off energy when your system is the one doing work. But if your system is the one whose work is being done to, or don ginagawa yung work sa system natin, then the sign for that is positive, because your system is gaining energy. Heat, the same way, the same goes in heat. If heat is added, the sign for heat is positive. When you add heat to the system, it's positive. And when you remove heat, the sign for that would be negative. Okay, so that's practically the first law of thermodynamics, the law of energy. The second law of thermodynamics, okay, deals with another quantity. Second law. So the second law of thermodynamics is also called as the law of entropy. So according to the law of entropy, or the second law, it tells us that the entropy of an isolated system almost always increases. So before we explain what this law tells us, let's first define, well, important terms like what is entropy. So according here, entropy is a measure of disorder or chaos in an isolated system. So it's the measure of, well, kaguluhan. Of course, as we will always observe, um, yeah, it's on the chaos in the system. So what does it tell us? So what does this law tell us? This law tells us that the tendency of all matter is to go from a state of order to a state of disorder, which is the natural tendency of all things. For example, we would have a room that is neat and tidy, like over here, neat and tidy room. And then after some time, okay, entropy would take over, and then it would go to a state of disorder. From order, it would go to disorder. Likewise, for many things around us, it goes from being fixed to being broken. You would have new shoes right now, but after some time, due to wear and tear and due to repetitive use, it would get worn out. So it goes from a state of order to disorder. So that's practically the law of the second law of thermodynamics, which is the law of entropy. Okay. So last but not the least, we have the third law of thermodynamics. So the third law of thermodynamics, that I don't really know what name it has, but the third law of thermodynamics is the following statement: the entropy of a system approaches a certain value as the temperature approaches 0 Kelvin. As the temperature approaches 0 Kelvin or absolute zero. So what does it tell us? It tells us that absolute zero temperature cannot be reached ever, 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 ever. So you cannot reach absolute zero. Why? Because according to here, whenever whenever we try to reach absolute zero temperature, entropy reaches a certain value. Entropy reaches a certain value. Okay? Because entropy, I forgot to tell everyone, entropy is directly proportional, by the way, to temperature. Entropy is directly proportional to the temperature of a body. Forget the sign. Oh, it's S. The sign for entropy is S. Sorry. Okay, so, but you don't have to remember that. I'll just write down the whole word. So I forgot to say that entropy, well, is directly proportional to the temperature of a system. And so when you approach absolute zero, entropy approaches a certain value. Okay? Theoretically, when you have 0 Kelvin, entropy must equal to 0, but we should with that if entropy reaches 0, that is, well, a disagreement with the second law, because according to the second law, entropy always increases, it never decreases. So 0 Kelvin cannot be reached because in the first place you cannot reach 0 entropy. So that's practically what the third law tells us: absolute zero temperature cannot be reached. And because of that limitation, that absolute zero cannot be reached, you cannot construct perfect heat engines, which wouldn't be the scope of our topics anymore. So that's all of it for today. So that's all about the laws of thermodynamics. I hope you learned something from that. And that's it for today. Goodbye and farewell. Have a nice vacation.